data logger, and you can try it out or solve that assignment, right? That is going to give you a little bit more insights into what happens in such systems and how the different factors that we were kind of recording, right? Like signal is to noise ratio, or the number of satellites that were available or that were visible at a certain point in time in a particular location. How does it impact the accuracy of the localization, right? Or how does the GPS error sort of depend on that, right? So I mean, we have already sent you like whatever uh, ID, right? Whatever email ID you have registered with, we have sent an invite. If you still did not receive it, we are going to send it again, right? So we will make sure that you get that Google group invite, and irrespective of that, we will also share the YouTube playlist, right, where we are putting all these lecture sessions. Okay, so uh, with all the registered participants, we are going to share that link as well as any other assignment that can come up. So I'll probably give you one more assignment that covers today's and tomorrow's class. So you can give it a try. And if you have any issues in solving that assignment, or if you have any issues that you want to share, right, there is something you feel is not right, you can always share those insights with us, right? And do not email to the NPTEL team, right? That is the elearn thing. You can send me any things that you want to share in my personal email ID, right? The email ID shared in the website also is ayon at the rate cac.iitm.ac.in. Okay, so let me directly go to the today's slides, right? So today we will have a little bit more to cover, right? We started with whatever we have learned in the last class, that is the GPS technology, right? And some of the principles that we learned yesterday was the range equations and how do you solve range equations in order to obtain the location of the device, right? So we have looked at one version, right? How we could do linearization using the Taylor's theorem, and then ignoring the higher order terms, we just ignored the second order term onwards, right? And that was a trick which we played to linearize those equations, and then from there it was straightforward. It was a system of linear equations, and each equation was obtained from a given satellite data, right? So for every satellite we had a range equation. So we are going to carry forward that concept, and we are going to look at other ways also about how to obtain the or estimate the location of the device. Okay, so as you know, right, indoors we do not have access to GPS signals, right? So it's not always the GPS satellite information that we will be able to obtain, but what we can imagine is inside our homes or in places where we call them as GPS denied environments because GPS signals are not able to reach. We can think of these pseudo satellites, right, which are basically things like your uh, which could be things like access points or cellular base stations, right? So these are Wi-Fi access points, right? Wi-Fi access points could be uh, references in our coordinate system. If you remember, in the last class we discussed about a coordinate system, and in the coordinate system we had like two things. One was there has to be some place that we call an origin, right? That is 00, and apart from that, we also need some reference points. So those reference points or anchor points, or like often we call them landmarks, right? We have to have some devices that could help us or that could emulate the pseudo satellites, right? It could be Wi-Fi access points, it could be cellular base stations, even it could be other modalities like a speaker, right? So often we can use acoustic ranging where it's no longer an electromagnetic wave, but it's a sound wave, right? So we can have a speaker, right? And on the receiver side, instead of having an active radio transceiver, what you will have is basically a microphone. It can always be a radio, right? There's a radio device, which is of course useful for RF communication, which is for most of the different modalities we can support, like cellular base station will require some kind of a cellular radio, Wi-Fi base station or Wi-Fi access point will require a Wi-Fi radio, and and then like GPS is going to have a GPS receiver. These are all radios. On the other hand, you can also conceive systems where the distance or the pseudo range that we discussed yesterday, like if you remember row 1, row 2, where the pseudo ranges we obtained from the GPS signals, right, by correlating it with the gold code and trying to find out the offset. Here also there are different methodologies where uh, that could be used. Okay, so we will look at those kind of technologies today. So just to complete this thing, you can have a speaker microphone setup as well, in order to find out the range in between the what I call as a pseudo satellite or an anchor and the device. Okay, and we are interested in finding out the location of the device. So this is a smartphone that I've shown in this picture. So XY is something that we want to estimate. Okay, so we want to estimate this. Okay, and what are the inputs to this problem? The inputs to this problem I have shown on the right hand side. There are two fundamental things that are required. Okay, so one is ranging, right? Ranging is the process in which you obtain the distance in between the anchor and the device. Okay, so and it's not just one range, right, as I have discussed in the last class, and you have already kind of understood why it is required, based on the dimensionality of the space, whether it's a 2D space or whether it's a 3D space, how many unknown variables you have in the system, right? So whether there was any clock drift, right, that we corrected for, based on that you will need that many equations to at the minimum, right? So if you have more and more noise, you might require more, but at the minimum, you will require for a 2D system here, you will require at least 3 equations. Okay, so the first thing that you require is ranges. Okay, so there has to be a process in which we are going to obtain such ranges from these devices, and we are going to look at how to obtain ranges today in like great depth. Okay, and the other thing that you require also are the location of the anchors. Okay, if you remember, if we are using the in the range equations, we are using something like xi minus xu whole square plus yi minus yu whole square, right? So xu and yu, let's say that is the coordinates of the device that needs to be tracked, and xi and yi and zi basically is a 3D coordinate of the satellite. So in this case also, we need information about the anchors, and in particular, I would write this is as a location information. Okay, these are basically your reference points. So reference points come with a location information. So these anchors, you already know what is the location of such anchors. Okay, this could be x1 and y1. This could be x2 comma y2. This could be x3 y3 and so on. Okay, and this will be x4 y4. Okay, so these are the location of the anchors, and apart from that you need these ranges, and in that way you can find out the location or estimate the location xy of the device. Okay, hope the premises are clear, right? And you all can and all recall the range equations, right? I'm going to repeat this, but given we had some context in the last class, you should be able to recall what range equations mean. Okay, so that is the key to solving the this optimization problem that gives you an estimate of xy, right? That is the crux of a basic localization system. Okay, if you have the ranges, if you have the location of the anchors, you can go ahead and solve the range equation that gives you the estimate of xy. Okay, so now it might not always that be the case that the ranges are perfect. Okay, so on the left hand side I have shown you an example where the ranges are perfect, right? So if you write the range equation, you can solve it exactly. Okay, so if you just I will show you some ideas on how to solve this equation in other ways also, right? But some of these methods do expect that they treat these equations as exact equations and try to find an exact solution, right? Sometimes it is not an optimization problem that we try to like minimize some error, let's say using least squares and so on, that we'll also see. But the problem is that those kind of methods is needed because you have noisy ranges, right? So this is a perfect range, and this is a very idealistic condition scenario, right, which is rare. This doesn't happen. Okay, and most of the methodologies that are employed to find out the exact solution to the range equation, so let me write down, these are the exact solution of the range equations, right? So these are employed in such cases, right? But this will fail when we have noisy ranges. Okay, uh, may fail in the face of noise. Okay, so as we will see later, right? So the ranges are not available just by magic, right? There has to be some algorithm, some technology that are actually working under the hood, and we will figure out how these things work in order to obtain such ranges, right? So whatever range you obtain, it is not going to be precise to the like millimeter scale or even less than that, right? There will be some kind of an uncertainty in that range, and not only uncertainty, the fundamentally whatever technology that you are employing, let's say you are using some wireless transceivers in order to find out the distance in between the receiver and the transmitter. There are some fundamental limitations, let's say based on what the frequency is being used, what is the bandwidth of the signal. Based on that, what you will have is there is some limitation in the granularity, right, or the precision of the range, right? It cannot be, you cannot say anything which is more granular than, let's say, half a meter or 1 meter, right? So fundamentally there is some restriction. Okay, and that is going to add some kind of a noise. Okay, so this ring there, or this circle that I have drawn on the right hand side, is no longer going to be like, looks like a circle, because there is some uncertainty that are involved here, right? So if it was just an offset or an error, right, that is deterministic, we could have drawn a circle, right? But in this case, there is some kind of a standard deviation that is also coming with this distribution, right? So that error distribution has a certain mean, right? Even if the mean is 0, you can have a spread, right, or some kind of a variance or a standard deviation that is associated with the range. Okay, so your range could lie anywhere in this particular ring, right? That is how the distribution of the error of such ranges are modeled. Okay, so you might have a mean error, which is basically mu err, right? And at the same time, you can have some kind of a spread of this value, right? So there is a sigma err. Okay, so this tuple could be used for having a generative model for such distributions, right? You can have a generative model for such noisy ranges, right, which you can use for simulation, for example, right, if you want to simulate such the behavior of such systems, right? I'm going to take you through a small simulation that we have created, right? But this is something that you can also replicate and try out. So noisy ranges, and we have to, of course, employ some kind of optimization techniques in order to figure out the value of the or the best estimate of x and y, right? So I'll show you two ways, right? One using matrix algebra that also takes care of such a problem, as well as by using a nonlinear least square algorithm. Okay, so what exactly the equation should look like? the range equation with the errors. So let's say there are k beacons or anchors. So beacons is some term that we will use sometimes in place of anchors or reference points. So k beacons at positions xi comma yi. So treat them as your satellites. Okay. So in this case, A, B, and C, we have three beacons. Assume the node 0 has position x0, y0, x0, y0, and so on. Okay. So the distance measurement between node 0 and beacon I is Ri. Okay. So this is your node 0. You can have many such nodes. Okay. And the position of that is x0 and y0. Okay. And the distance measurement, we have just defining the terminology here. So rho or ri or d, whatever you want to call it, basically this is the range in between the device and the transmitter or the beacon. Okay. This is the your ri. So what exactly does this optimization problem try to solve? If you see xi minus x0 whole square plus yi minus y0 whole square, this basically is the Euclidean distance in between the devices, right? In between the beacon and the node. And what is Ri? Ri is the estimated range, right? Ri is not the true range, right? Because Ri is something that we are measuring, or we are, let's say, measuring, okay, or estimating, because it's not a direct measurement that we are going to use a scale and measure it. We are going to use some other proxy, right? Some other technology that we will be seeing in how to measure this. Okay, so this is a range estimation. Okay. And of course this ri value is going to be close to this on the second part, right? Whatever we have, square root of xi minus x naught whole square plus yi minus y naught whole square, right? It will be close, but it won't be zero. If it was zero, then your estimation was perfect. There was no error that was associated with the ranging process. Okay. So ideally fi should be zero, but it will not be the case because of noise in such measurements. Okay, so what I would like to do is that if we get a lot of measurements like this, and we try to see for what value of x0 and y0 or x0 y0, it basically fi could be minimized, or summation of fi could be minimized, or fi square could be minimized, because you could have some cases where fi is negative and positive, right? So we want to either take the modulus of fi, right, and make it minimum, or use a square value. Okay. So we want a summation of positive terms. Okay. So ideally this should be zero, and we have to try to play with the values of x naught and y naught, trying to make it close to zero, or we will be satisfied with some kind of a global minima. Okay, so there are chances that you could be stuck in some kind of a local minima, because let's say depending on the value of x naught and y naught, right? So let's say this is your 2D Cartesian space. This is x naught and this is y naught. You can have any such values, right? And think of this as a heat map, right? So for every point in this grid, right, you will have a value uh, of the function f, right? So there could be some places where the value is like really low, right? Maybe the solution is somewhere here. Okay. And there could be some places where the value is really really high. So I call it like I can use the color red, right? So this is really the value is very high. So okay. And there could be some places where it's like yellow, okay, where the value of the variable, or the value of sigma fi square, that value is less. So what we are trying to do here is that for what value of x naught and y naught I can minimize this sigma fi square. So maybe this is the place where like this is the value of x naught and this is the value of y naught, that actually uh, minimizes this particular sum. Okay. So in that way we could be even stuck in a local minima. Maybe we are searching in this particular location and trying to figure out the value, and we are not like we are kind of like my optimization algorithm is stuck there, right? So that is what in is the local minima problem in this context. Okay, and it could also be a three-dimensional space. It might be x naught, y naught, and z naught also, right, where the device is kept in a three-dimensional location. Okay, hope you understand the objective function, right? Are there any doubts regarding this objective function? I could clear the doubt right now, so that because most of the things that are going to come up is completely based on this concept. Okay, so if there are no questions right now, so let me proceed, right? And today I'm going to do a little bit more interactive session, because postponing some of these questions are not going to help us directly, right? Because if you have any doubt, please try to clarify that then and there, right? I'll try to keep it short, but let us not have a half understanding and proceed through the slides. Okay.
Sir,
Yeah.
here we are trying to find out the positions of the beacon or the position of the node, so as to
Position of
mean.
the node, position of the node. So beacons are there. It's already, this is given. So
Okay,
these are like your satellite, right?
right.
I mean, if the satellite location was known or the beacon location are known, right? And this is something that I have repeated here, right? So the anchor or the beacon location, these are known. Ranges are known. Okay.
Okay, okay.
So we are primarily trying to figure out this unknown, which is x naught and y naught, the red color thing. Okay. So that is the problem of localization. We want to figure out the location of the node. Yes. Somebody else, you want to ask something?
Sir, again, one more query, sir.
Yeah.
Sir, like only like a two-dimensional is sufficient, or we have to compute for the three dimensionals?
No, you can do three-dimensional. It's just that an additional thing that you have to do, right? So zi minus z naught square, right? The equation doesn't change a whole lot.
Okay, because it will show that is Euclidean distance, what you mentioned.
It's an Euclidean distance, right?
Yes.
So as many dimensions as you feel like, three dimensions you can give here, not an issue, right, for an optimization.
Okay, so it is not compulsory, sorry.
I mean, it depends on you, right? Whether your application is 2D. Most of the cases in like indoor environments, you don't care much about the 3D, because 3D is less granular. We just care about which floor, maybe first floor or second floor, right? So
Yes.
yeah, depends on your application of choice.
Okay, sir. Thank you.
Okay. So let me.
Excuse me, sir. So
Yes.
one more question. Here, this error calculation is done with respect to one node only, one beacon only. So
Not
is it sufficient?
one beacon.
Or
So I have used the subscript I, right? And this, and I
is,
have also used the sigma. So I is going to be from 1
there
to
is one
at
to
least,
oh,
yeah,
okay,
at least greater than equal to 3.
So one more question, if I may ask.
Mhm.
So Ri is the estimated location, right?
Estimated range, sir. Estimated range.
Range. Okay.
Location is x naught, y naught, right? Location is a two-dimensional value, x naught, y naught, or x naught, y naught, z naught, right? Some 3, 2, 4, 5. Ri is 15 meters, Ri is 20 meters. This is your estimated distance, estimated range. I have drawn on the left-hand side. See, in between A and B, you have Ri.
Thank you, sir.
Okay. So now, see, ideally we would, as I told you, ideally we would like the error to be 0. So fi is equal to xi minus square root this thing is equal to 0. And if we do some rearrangement, right? So take a square and then try to do some rearrangement, you can get this particular equation, right? So you can try to simply do a square of this, take Ri on the other side, square both sides, and expand the terms, right? So it will be x naught square plus y naught square plus x naught minus 2xi, y naught minus 2y minus Ri square is equal to xi square minus yi square. Okay. And in all these cases, please note that xi, yi, ri, these are known values. In the sense, you have access to such values. It could be erroneous. Erroneous does not mean that you don't have access to those values. You have erroneous estimates of those values. Okay. And if you keep on subtracting equation number 1 from equation number 2, because all this depending on the value of I, you could populate several equations like this, right? You can have equation number 1, which is going to deal with x1, y1, equation number 2, equation number 3, equation number 4, and so on, right? And you can use as many equations as you feel like, because as long as you have a lot of noise in the system, more number of equations are going to bring down the error. Okay. And of course you cannot solve this thing just using 2 equations. Okay, you need at least 3 of them. Okay, so subtract the last equation from the previous ones. So you can subtract the equation number 3 from 2, 4 from 3, 1 from 2, and so on, so that we have get rid of the x naught squared terms, right? Because this is what we are trying to solve for. X naught and y naught we are trying to solve for. We are trying to linearize this equation, because if we have x naught and y naught square, this will be a quadratic equation, non-linear equation. We are trying to make it linear. So earlier, if you remember, we are just using Taylor series to make the equations linear. Here we are just simply squaring the objective function, trying to manipulate by subtracting one equation from the other, and in that way we get this linear combination of these terms, right? Note that this is a linear equation in terms of x naught and y naught, and this entire part on the right hand side, let it look very cryptic, right? But this is known, this is just a number. Okay, so Ri could be 15 meters, Rk could be 27 meters, right? Xi could Xi and Yi, right? So this could be like, let's say 3,2. Xk, Yk, it could be 7,9, right? So these values are known. So Xi, Yi, Xk, Yk, these are like beacon locations. Okay. Here also this is known, this is known. So only the red part that I have written here is are the unknown values. Okay, so I also hope that this linearization is clear. Now again we have a set of linear equations, and that is obtained from a set of range equations. Okay, then the range equations are quadratic, definitely. Okay, so this B is known because B looks big, this matrix B. As I told you, it is composed of known values, and we can simply write this as Ax is equal to B, where A is the matrix, this one, right, that is shown on the right hand side. This is also known. Okay, so if you have an exact solution, right, and that will not require you more than three very like three equations, right, or 3 beacon locations. In that case, you don't want to make it an over like deterministic system. If there is no noise, just 3 equations are fine, and you can simply find out the value of x by from this equation, right? You just do an A inverse, take both sides, you do an A inverse V, and in that way you can figure out the value of x. Or what is x here? This is the vector, which is that is the location of the node. Okay, so node is the device location, or node is basically the device whose location we are interested in. For now, assume that the beacons are all at known locations, beacons or anchors, reference points. I am repeating it for so many times, right? So those are at known locations. So these are all beacon or anchor locations, and I'm going to stress out that this is known. Okay, and we have solved for the unknown, which is x. This was unknown. And also you can have noise in such systems, right, where there are standard methodologies to solve for the value of x, and in that case you can use this equation, right? And we don't want to go into the details about how this equation can actually help you solving for least squares, right? So instead of giving an exact solution or not giving a solution because of noise, you can use something like this: A transpose A inverse multiplied by A transpose B, right? So A is known here, B is also known, but the catch here is basically is that there is noise in all of them. So not only just the ranges, your location of the beacons could also have some noise. So once you say that your beacon is located at 3,2, it might be actually 3. 17 and 2.09, right? This could be the exact location of the beacon, but you think that this is the location of the beacon, right? So that also introduces some kind of a noise in the location of the anchors themselves. Okay, so and range, as you know, that range will also have noise. Okay, so I am hoping that this is absolutely clear, right? And you can try out yourself, because this is just you can take the transpose of this matrix, you know how to take an inverse of the matrix and do matrix multiplication, right? So this is something that everybody from your background should know. Okay, so you already have now a tool to solve this yourself, right? If you are given a set of beacons, if you are given a ranges, very easily you can figure out the value of x. Let it be erroneous, because if I am giving you erroneous data, x will be erroneous also. But what we are interested in, how erroneous is x. Okay, so if you increase the number of equations, right, if you have more and more number of beacons, you can try out and see for yourself that how the difference of the estimated x and your real x is going to come down, right? So you always have to look for an error. So here we call it a localization error. Okay, localization error is what we can call this an x cap, right? Because this is an estimate of the location. So if your true location was x and your estimated location is x cap, so what we are interested in is basically the distance, the Euclidean distance in between x and x cap, right? So this will be something that we will be interested in. Okay, and how this relates to the number of anchors or beacons. Because if you increase the number of beacons, that noise is going to be distributed across all these equations, and uh, that is something that might help you to get a better estimate of x. Okay. So now there are other ways, right? I'm going to also introduce you to another technique, just for solving this as a nonlinear least square fit kind of an approach, right? And just revisit these range equations. You again come back to this fi is equal to ri minus root over of blah blah blah. So this gives you the, again we go back to square one. We, instead of doing a linearization, we try to keep this equation as it is, because sometimes why I'm teaching you this, right, sometimes it might be very tedious job. Like suppose you have a very complicated equation, and in those cases it might not be like very much worthwhile to sit down and try to linearize it, right? Sometimes it might be worthwhile, but sometimes the equations are such that it is very difficult for you to linearize them. Okay, so you can of course follow the Taylor's theorem, right? That is one very powerful tool that could be used. But you can also keep the equations as it is, right, in the nonlinear form, and then try to solve it as an optimization problem. Okay, so how to do it, right? So one algorithm, right, that we have is known as this Levenberg-Marquardt algorithm, right? So what exactly is this? If you see the primary application of this LM algorithm, we'll often call it LM. We don't pronounce this. Complicated for us to pronounce all the time. So LM algorithm is the least square curve fitting problem. Given a set of, concentrate on what is the statement here. Given a set of m empirical pairs xy, yi of independent and dependent variables, find the parameters beta of the model curve function of x beta, so that the sum of the squares of the deviation is minimized. So that is exactly what we want. We have some empirical pairs xi, yi. So this is written in a more mathematically concrete format. I am going to help you in kind of intercepting this thing, right? So we have this empirical pairs xi, yi. Don't confuse this with the coordinates, right? So we have xi, which is in this case, in our case, this is the anchor location. Okay, anchor location, and yi is basically your ranges, right? So it does not restrict you in trying to or like kind of dimensionality of xi or yi. Xi could be multidimensional for our case because or like 3-dimensional, 2-dimensional, whatever is our system. So xi for us could be something like capital Xi, capital Yi, capital Zi, and this Yi could be some kind of an Ri. Okay, so what we are supposed to do, we are supposed to find out some model parameter beta, right? So in our case, beta is basically x naught y naught. That is what we are trying to find out. Okay, so this is just a mapping of the statement of the LM algorithm, and we are trying to put it in our context, whatever we have already learned. Okay, so argmin basically it's trying to minimize the value of this equation and trying to figure out for which value of the argument beta it is going to achieve that. Okay, so beta is basically your model parameter, and model parameter is your unknown location, sorry, the unknown location of the node. Okay, so this is what we are going to uh, find the optimal value of, right? So this is your parameter, and yi is the same thing. In our case, it is going to be the range. And what is this function? Can somebody tell me what this function is? What is this function? What is this function in our case?
Objective function.
No, but what is this function in our case? Objective function is the entire thing.
Estimation of ranges.
Range estimation, like the Ri minus square root of that.
No, this function there is no Ri's. Okay.
Okay, sir.
This function is simple Euclidean distance in between the node and the beacon. Okay, so this is the range. Okay, don't get confused. I mean, this is why I'm spending some time, because this is something that you really need to understand in order to solve such range equations, right? What I have written in a different language, we have actually written the range equation. Okay, and if I again rub this out, right? Let me rub this entire thing, right? This is the thing that we have to solve, right? The LM algorithm tells me that this is the skeleton, or this is the structure of the equation, and you are free to imagine different components of this equation, right? For our case, it suits best if yi is a range, and xi is basically the location of the beacons, and beta is your unknown location. So this is your model parameter. Okay, because like if you have any background in simple ML techniques, like basic second year, third year ML techniques, right? They'll always talk about fitting a model, okay, or fitting a curve even, right? So in that case, it depends on how you like get different values for the fit depending on your input parameter, which is beta in this case. Okay, so even if you don't understand it completely, try to ponder over this thing, and we are going to give you examples, and I'm also going to show you a code that actually can demonstrate this idea. Okay, I request you to actually implement this, right? So I have already given you enough background on the mathematics, right? I'm also going to get you run through the some code, right? So that you would be in a good position to implement that, right? So one idea we want to do as a part of this workshop is actually make you ready, not just with some of the theoretical concepts, because unless and until you do this, right, and you appreciate or you get kind of satisfied by looking at the performance, you start playing with these parameters, right? You won't retain this for long, right? Unless and until you use it, right, solve some exercises, you will start forgetting about this. Okay, so quickly some code, right? So anchors are basically so on the top left, just concentrate on the top left part of the screen where I have defined anchors locations, right? So this is a simple Python fragments of Python code that we have written. So this is your location of anchor 1, this is the location of anchor 2, and this is the location of anchor 3. This is a 2D system, Okay, so we just assign only two coordinates for each anchor, and we are just using some integer value. Okay, and ranges are basically the three ranges that we will get from these three anchors. Okay, range 0 is the distance of my node from anchor 0. The range 1 is basically my distance from the node to anchor 1, and range 2 is the distance of from my node to anchor 2, right? So you can say this is an anchor 0, this is anchor 1, this is anchor 2, this is range 0, this is range 1, this is range 2. I think it is absolutely clear, right? So X is basically the inputs that we have from the system. If you remember in the very first slide, we spoke about this thing, right? We have anchor info plus the range info that goes to my localization algorithm that spits out this value xy. Okay, we are just programmatically viewing it. Okay, and for there is a good news that there is a very nice library, right? Earlier we used to use the scipy library for doing such optimization problems, but there is a separate library just dedicated for solving such nonlinear least square minimization problems, which is known as lmfit. Okay, this is a Python library. Okay, and the good news is that this is actually inspired from this thing, right? This lm method, right, that we just saw now, right? So this was the starting point of this library, and it was a lot of extra things that actually went in to optimize the solving of such equations in a better way. So if you take a look at the different functions that are available in this lmfit library, you can try to use them and get more acquainted with that, right? So what we do here is basically your curve fitting or the least square optimization. This is optimization step, which is basically one line. So the time I'm spending, all the time I spent is basically trying to make you understand why we are in what process we are trying to do this optimization, right? I could have just simply given you this thing lmfit dot minimize and it does some minimization, right? What we are minimizing, you should be absolutely clear. Okay, we are trying to minimize some kind of an objective function. We have defined the objective function, I'll come to that. We have a model parameter, and the model parameter is basically the beta in case of your lm algorithm that I have discussed in the last slide. That is your location. Okay, and you have given some arguments or inputs to your function, objective function, or this is cost value in this case, which is x. What is x? X is an array that contains anchors and that contain ranges. Okay, and now once you solve for this particular thing, right, so you will get this log estimate, right? So and from that log estimate we are going to have it is going to contain the values of xy, right, or the location. Okay, and then you can write your own equation to, or write your own code to find out the error, right? If you knew what was the ground truth location or the actual location of the node, you can always find out the distance in between the location estimate and the actual location that is going to give you the error. Okay, and the cost value is basically the optimization function. Okay, so what is the function that we are trying to optimize? And this is something that we have been discussing for so long. And for every anchor, so you just concentrate on this loop, right? And I would request you to, this is a code that we have written in the fragments of the code I'm showing you, but you should ideally try to write a full-fledged code, right? And I am going to help you in guiding you how to sort of think about evaluating such a system, right? And I'm going to also give an assignment on that. Okay, that will help you in order to have an end-to-end understanding of not only just the algorithm behind it, but also how to implement it. Okay, so for all the anchors, what we are simply doing, we are summing it up, right? You remember we had this sigma. Okay, and this sigma was summing up my objective for individual range. So for how many number of anchors we have, we are going to run this particular loop. And what we are going to add, we are simply adding the distance of I from this xy, right? So I could actually give you the location of the anchor, and location x, location y is basically the, this is the model parameter, right? So this is your beta, and beta is basically having two components, x and y. Okay, So the distance in between I is basically your anchor location, comma, right, comma, location X, location Y, which is basically your model parameter. Okay, so this is the distance, like the Euclidean distance in between my node and the Euclidean distance in between the anchor and the node, had it be in location beta. Okay, had it be in location beta, I don't know beta, I am trying to solve for beta. Okay, so had the location of the node been beta, what would have been the distance between the node and the anchor? That is the distance of I comma location X, location Y. Okay, minus ranges K. So what is ranges K? Ranges K is the distance that I have estimated, not the analytical value of the range. I have estimated in between the node and the beacon, right? What is the estimated range or measured range? Okay, and then we basically do a square, right? We don't want the sum to be impacted by negative values, right? We just take a square of it, or you can take an absolute value and sum. Okay, so this basically becomes your objective function, and we are summing it up. As I told you, we are summing it up. So what is my objective function now? We are taking the distance in between the anchor location, comma, beta, that is my model parameter, minus the range for that particular anchor. Okay, and square of that. So we are telling the LMFit library that take this is my objective function. Please take it and give me minimize. Try to minimize that, because I have used lmfit.minimize. So it is going to take this cost value and try out different values of location, or try out different values of beta, and in the process it is going to minimize that and spit out the value of beta for which it thinks it is not like completely, it might not be completely optimal, right? There could be different local gradients and so on, local minimas, local maximas, and so on, right? So you can try out different methodologies, right? That can take a long time as well. So if you want to implement this kind of a system as a real-time system, right, that wants to give you a location update every few milliseconds, you cannot solve a very complicated nonlinear optimization problem and spit out the values every time independently. Then you have to play some trick, right? Maybe you can use the previous computation and help this LMFit equation with an initial guess. Okay, you can start, you can have a guess of the initial values of beta, right? So those kind of things are possible, and I would request you to look at the library in a greater extent. Okay, so for a demo, we have like one of our group members in our lab has implemented a demonstration, right? And this is something that I am going to show you, right? And try to concentrate on the different aspects of the error, right? And how this particular error is going to impact the value of the estimated location, okay, or the estimated position. Okay, so just uh, let me know that whether you are able to view the screen. Okay, is the screen visible?
Yes, sir.
Okay.
Yes, sir.
Yes,
Yes,
sir.
sir.
So you see a white canvas, right? And here, the software is designed in such a way that I can place anchors as I feel like. Okay, anchors is basically anchors of the beacons. So I placed one anchor, right? I can place one more anchor, and let's say I place one more anchor. So I have placed three anchors. What is the good part here? I know the location of the anchors. Okay, please note that maybe the font is a little bit small, but I guess you'd be able to understand that I have mentioned some coordinate value for the particular anchor location. Now, let's say there is a point I want to get the value of the location for. Okay, so I have deployed a node at 534, 348, right? And we have perfect values of ranges. There is no range error, and the ranges are basically given by this circle. Okay, so if you think, if like if I know that the range is, let's say, 181 in this case, right? So 181.5 means the point could lie on anywhere in this circumference of the circle, right? So same for the second one and same for the third one. Okay, so if I give you a value of range and one anchor, this can lie on anywhere on this circle. Same for the other ones. So what your solution geometrically means is basically you are trying to find out a location where these three circles intersect. That is the geometrical interpretation of solving this equation. Okay, so you have gotten an analytical idea, you know how to code this up, but geometrically speaking, visually, what does this mean? Okay, so this is going to give you the point of intersection of these three circles. And what you can do now, you can start disturbing the system, because we have the optimization running in the back end. So what I can do, I will just try to disturb the system. I'll be a little sort of bad guy, right, and try to put some noise in the ranges, right? So I have two things that I can do here. One is that I'm basically picking up the noise of the range from a distribution which has a mean and a standard deviation. Okay, as I just now told you. So if I add some kind of mean, right, let's say I have an error of 5 meters, right, let's say some 4.88 meters, and then try to move it, right, we might not see a lot of error. So the error is basically 5.83. so if you see the estimated position of the node, it has shifted a little bit, right, because the ranges that we have supplied are kind of erroneous to the extent of 4 to 5 meters. I can increase the error, right? And if I increase the error, the LM fit is, let's see, there is no particular point where these three circles intersect now. So there is one circle, big circle, there is the top slightly bigger circle, and there is this bottom circle, right? So there is no single point where these circles intersect, because now if you give this to that the simple matrix, right, the kind of solutions we were seeing in the very beginning, they will say this is an indeterministic set of equations. They don't that you cannot determine an exact solution based on these equations, right? But while we try to solve this via this nonlinear optimization kind of an approach, nonlinear least square, we are trying to fit, right? We can try to get an approximate solution. Okay, this is not an exact solution, but it does not throw up, right? It does not tell that, oh, I am not able to do or solve this problem. Or we can do something reasonable. Of course, you have so much 96 meters error, or some in any unit you can consider maybe 96 centimeters error is there. So the error that is produced in position is 113.53, and if you can move this, you'll be able to understand, right? In many such situations, this error can vary. Okay. And now, apart from the mean, you can also add some kind of an uncertainty. Okay. So uncertainty is the width, right? The spread. It can be 96 minus sigma to 96 plus sigma. It can be anywhere in between that. Okay, and that is also make your position estimation worse, right? And there is enough evidence, right? If you can simply play with this to see that how the not only just the values of the error, right? The error, I know this 96.75 is basically your mean range error, and the standard deviation of that range error is 24.44. But if you see that the error is not constant, right, the error in position, I am showing it on the right hand side box, right? There is an estimated position and there is an error in position. It keeps on changing based on the true location of the node. Sometimes it is close. So in this case, right, where it is perfectly inside these three anchors, right, it is close. We don't have a huge error, right? When we go far, right, or we go sort of outside, right, so the error increases. Okay. So are there any questions you have regarding this demo? Because if some of you are not able to understand this, right, I can help you understanding it properly. Right? Are there any queries regarding this demonstration? It would be better if you speak up, because I cannot see the chat simultaneously.
So mean error is kept fixed, sir.
Yes.
this analysis?
Yes. I mean, we are picking up the values of the range error. So mean, when you say mean error, it's a mean range error, remember, okay?
Okay.
So the range error is, how is it obtained? It is obtained by adding some noise to the Euclidean distance in between the node and the beacon, right? So if the distance is d, we are doing d plus epsilon. And epsilon is basically picked up from a distribution that has a mean 96 and standard deviation 24.
24.
Okay.
Okay.
And that's why we have this fat kind of rings, right? Not just a circle, because if we have a standard deviation 0, I am very deterministically picking up the value of noise as 96, right? Which is not the case. We have some uncertainty with that also. Okay. And if you think my solution should lie in the location where these three circles sort of intersect. Okay, in this location we have the three circles that are intersecting, and that would be the possible value of the estimated node location, right? And so my LM fit is doing the job pretty well, right? And sometimes it completely fails, right? Sometimes the error is very, very high, and it is not the problem of the algorithm. It's the problem of the noise, and so much of noise is there. And you can, even if you are given this task visually, right? Suppose I hide the node from your site, right? I don't show you the node, I just give you the ranges. Probably we'll basically figure out that, okay, this is the location of the estimated node where most of the three circle rings are concentrated. Okay.
Sir, there is a possibility that the node may overlap with the reference node.
The node may overlap with the reference. Yes, it may happen. Yeah, like this. One of the ranges is basically
Yes.
going to be 0.
Okay.
That is what you are saying, right?
Yes, sir. In this case, how to do that optimization, sir? Like,
I mean, the optimization doesn't care. It will just have 1 0. I mean, you are basically saying that one node is useless. So one anchor is useless.
okay, okay,
Right? This is same as not having that anchor, because that anchor is 0, not contributing anything to that minimization problem.
okay.
Thank you, sir.
Thank you, sir.
Okay.
Sir, in this demo, we are assuming that the anchor locations are perfect, right? There is no noise in the anchor location.
There is exactly, yeah. I did not add that complexity. That anchor locations are perfect. But see, if we say that the ranges are imperfect, it indirectly means that is also adding some. You can theoretically add some noise, right? Because end result is that your range would be noisy.
Yes, yes. Okay, thank you, sir.
Okay. So I mean, the expectation is that not just the visualization part, if you can ignore, right? You want to develop the back end of this, right? Given these values of anchors and given these ranges, you want to know what is the estimated position of the node and what was the error. And the visualization helps you understand or play with these different values of errors and standard deviation, right? So this is going to improve your insights on this particular thing. Okay, so you can make the standard deviation very, very high. Right now, see, it is getting like completely like very, very high range error. Okay, so in this case, it is same as lost.
Sir, I have one question.
Yeah, yeah.
Yeah, sir, can I get access to your tool that you are using?
Yeah, it is locally done. We have developed it. Yeah, I can. You can share that later.
Thank you.
Yeah. I mean, the idea is that I don't want to give the backend right now, because I want you to give it as an assignment, right? First, try to develop that,
Yes.
and I can give you this tool for you to play with, right? So that you understand what is going on. Absolutely.
Sir,
Right.
excuse me, sir.
Yes.
So why we are not finding time error, sir, delta t? Because, sir, we have 3 satellites and we have 2 unknowns, sir. But there is one
So in this
unknown.
case, what we are kind of doing here is that we already know that this kind of devices could be synchronized, right? And we did not come into the issue of how we are finding out the range. That we will come later. These are not really satellites, right? Now we are talking about things that are indoor access points or cellular base stations, right? And we are not assuming that they themselves are synchronized. Okay, so mathematically, if you have these 3 ranges, you can find out a 2D location. But how we are finding out the range is the problem that I am going to come now. Okay, So earlier we had an issue, right? The way we are finding out the delta t offset in between the signal that was transmitted and whenever we have received it, that itself had a problem because of the clock drift. The way
Yes.
we were trying to compute that or estimate that. So now we will see how we can estimate that in case of wireless systems, right? Then you will appreciate why we do not want to have a separate offset and solve it as a problem itself, right? So we will see that. Okay.
So
So
it
after,
means that for short ranges we can ignore the delta t because the time
I mean, the
time.
way we are yeah, we can ignore the delta t for this. The way we are trying to compute the range, it is going. We are always going to take care of the clock drift in that only.
Yes, sir.
Okay, so we'll incorporate clock drift, but that will be, the protocol is so intelligent that the range is going to be agnostic of the clock drift. Whereas in case of GPS, the range was not agnostic of the clock drift.
Yes.
Okay. Okay, so I'll come to the slides, right? And there is one more thing I wanted to show you. Let me introduce that particular concept first, right? So what about the location of the anchors? Okay, so can somebody like some of you are already seen, right? So depending on where the location of the anchors are, the estimation error was keeping on changing, right? Let's say this blue, red and green are the anchors and D is your device. Okay, so we have already seen that we can have a range, right? Let's say some range 1 plus some error, right? There is a range 2 plus an error, right? And then there is a range 3 plus an error, right? So this was helping us to estimate the value of the position of the device. So maybe we are saying that this is the location of the device, which is x hat comma y hat, where the location of the true location of the device was x and y, right? And the error that we were trying to figure out was basically x minus x hat plus y minus y hat. Okay, so this is your error. Now my question is that does it have any correlation with the geometry of how A's and the D's are together, right? So any implication on the geometry? Okay, so we will come to that, right? We can play with that particular demonstration and try to figure that out, right? So if you see, we had this GPS example that we brought up yesterday, right? And somebody was asking me what is an optimal way of solving this problem, right? So I have already told you, right? There is no direct way that I can manipulate the location of the satellites. The location of the satellites are given. I cannot do anything about it. And you cannot do much about the location where you need GPS data. You can always go to an open field and have a very accurate GPS data, but that is not what I want. What I want is that given like this place right in front of these two houses, we want the location to be accurate as possible. But the problem will be that from many different sides, because of the presence of these buildings or big trees or whatever, any obstacle, right, that is going to interfere with electromagnetic waves, they are going to cut off these signals. And this, in effect, these GPS satellites will be not visible. Okay, not visible to the receiver. Okay, receiver is your node or beacon, not the beacon, it's a node. Okay, the beacons of the anchors are your satellites here. So you are basically getting a biased view of where your satellites are, right? You are completely cutting off the satellites from this side. You are completely cutting off the satellites from this side. Okay, so think of these ranges as like strings, right? They were pulling with strings, right? Because there is a constraint that these uh, satellites were putting, because these ranges were the constraints. Now these are gone. The satellites are no longer there. So this set of devices, right, this set of nodes is free to sway this side or that side, because still you only, the constraints that you have is from this let's say the west side or the east side. Okay, So the north and south is gone. North and south, it is completely blocked off, and that is the reason there is no direct constraint from this side. So only thing is that I am basically think about a small kind of an object that is tied on the west side using a rope and tied to the east side using a rope, right? It is still free to oscillate little bit on the north and south part, right? And that is basically the geometrical interpretation of why these errors can happen if you do not have an uniform distribution of anchors on all sides. Okay, so if you remember, when I took the node in the exact centroid kind of a location of all the anchors, the error suddenly magically went away. Okay, so it was trying to optimize the problem to the farthest possible extent. Okay, so in this situation where I had anchor 1, anchor 2 and anchor 3, these are the A's, right? And then you have the node here. So it was doing a pretty good job. Okay, although there could be errors, but the optimization problem kind of figured out that okay, this will be somewhere here. Okay, whereas if you keep the anchor, if you keep the node here, right, it might actually have a pretty larger region of uncertainty. Okay, and this is basically a function of the geometry, the relative geometry of the nodes and the anchor. So it is basically, I would say, relative geometry of the anchor and node locations. Okay, so let me quickly demonstrate this, right, in the demo. So if you see here, can you tell me a situation when it really becomes poor, right? When what is the situation when the error is just going to be maximized? So common sense, right? When the area of overlap is going to be maximized, right? So if you have a very smeared area, right, that is being instead of an intersection, now you will have an area, right? Because you have this uncertainty in the range. That is the reason you have the standard deviation of spread, right? So they are not intersecting at a point given, but now their intersection is creating some kind of an area which is sort of smeared by this yellow circles, right? And my question is that when we are going to have a pretty substantially large smeared area, can you think of any situation like that?
Sir, when the three anchors are in one line?
Very good, very good. When the three anchors are collinear. So you can like simply test it out, right? If you have this collinear set of things, look at the space, right? Look at this entire thing, how they have actually lined up together and created this mirror area which is pretty large, right? And then that immediately started contributing to that error. Okay, now if we increase this standard deviation, it is almost like getting mad, right? So it's a huge this bright yellow area of uncertainty. Okay, so whereas if you simply give enough room or freedom for this to roam around, right? See, this has immediately the error has reduced. Okay, so if I keep it like enough, so think of these nodes as like people pulling strings. Okay, you have enough constants from all the side in spite of having so much of error, right? This 55-meter error we have introduced, 45-meter spread we have introduced, still my LM-fit that optimization problem was able to that algorithm was able to solve this optimization problem to a pretty good extent. I'm not saying that with this error introduced you are going to say something like 0-meter error, right? But now think about the situation, right? Simply if I take it here, right, and then take this one also, just remove this constant as well, right? So you'll see that in some cases it might work, right, but errors are going to increase further and further. Okay, so ideally it could be anywhere in this smeared area. Okay, so it actually depends on the distribution of the relative geometry of the anchors and the beacon, because basically you are trying to find out where these circles overlap. Okay, so there is a name for this, and you should know in this context, because you are studying location tracking, you should know the name, right? So I just gave you, I completely gave you what it means. Right now it is just the name that you have to know. So this is known as geometric dilution of precision. Okay, that's why I did not give you the fanciful name in the very beginning. Okay, so you have completely understood now that what is the context or what is the intuition behind this, right? So if you say that there are these two nodes, blue and orange, depending on where they are, the area of intersection of the circles are going to be different. Okay, so in this case there is a small region uh, in the top and the bottom, right? So these are the places where the circles intersect, and your solution should either be this or that, right? And you have a third anchor to do the tiebreaker. Right, if you had a third anchor, you can be pretty sure that it's really here, right, and not here. That is why you require three anchors. Okay, so but still, if you see that area, the area is quite large, and the error is going to be somewhat proportional to this area. Okay, if not the error, also the overall uncertainty or the expected error, right? Whereas on the right hand side, if you see the different rings, right, that are basically a function of this range, right? This is the range, true range, and then there is an epsilon, and there is also for this, the true range for the blue one, and then there is an epsilon, right? So if you see that the area of uncertainty is pretty much like high. Okay, it's a large area, so this is highly uncertain. You may be lucky enough, right? You may be lucky enough to get a location which is like closer to this. Maybe your node is located here, right? You may be lucky enough to get something here, but that is not always the case, right? Depending on how the system is initialized, how many iterations you are going through, you can end up in a situation where your node is predicted to be here or here. That is also possible. Okay, so what I'm only saying, the expected value of the error, right, the expected value of the uncertainty is going to be dependent on the relative geometry of the nodes. Okay, so now I have shown several situations where a1, a2, a3 are on the three corners of a triangle, and T is basically the target device. Okay, the target device's location we are interested in. So this place is pretty small, and now a2 and a3 are closer to each other. T is outside this triangle. This has become a little bit larger. Okay, so in this case, if you see, there are like two places, right? One a little bit on this side, little bit on that side, right? So it depends on where most of the circles intersect, right? And in case of the fourth figure, a1, a2, a3, this is completely smeared up. Okay, so even if you try to solve the range equations just based on the geometry of the nodes, you can actually face a different value of error, or on an average you can face a different value of localization error. Okay, so this is known as dilution of precision, and this is primarily, like, empirically you can think of it as an output location divided by the measured data. So measured data is basically all the points that are in the gray region. We have measured them, right? So it can be anywhere, and where it is highly probable, it has to be somewhere here. Okay, so this is your output location. So if kind of this is the ratio is going to give you an intuition about what is the dilution of the precision is going to be diluted by the presence of the noise in the range, as well as the geometry of the node. So in this case, this is going to be this triangular kind of a thing, right, an area. So this entire place would be the output location anywhere here, because the noise is not allowing me to get any more precise. Okay, so whatever you have given, the data you have given, my precision is actually bounded by the noise which is there in the range, the theoretical noise limits, what is the spread of the data in terms of the standard deviation we have used, and the geometry that is given that we cannot do anything better. Okay, so on an average it has to be the precision will be limited here. I cannot say that I prefer this point with respect to this point. Okay, because both of these points are going to create similar values of the objective function. Okay, so keep this in mind. So we learned how to go about the range equations, solving them. We saw several ways to solve the range equations. We looked at some code, right, that you can use this library called lmfit, right, and you can find out the error, right, and then you can start playing with the location of the anchor. Say I want to place it in the same straight line, collinear, right, I want to place them in a circle, in a triangle. Increase the number of anchors. Don't just limit yourself to just 3 anchors, right? We can simply check out what happens if we have multiple anchors. Okay, so in the screen, right, if I just keep on increasing the number of anchors, right, so this is just the 3 anchors with substantial noise. Now if I say that I want to place more anchors, right, see, if I place more and more anchors, my error reduces. Okay, so my whatever huge error I have given, this error is sort of teased out from different directions, right? Now it doesn't matter, right? Even with a large value of error, we can still see a very good precise estimate of the location, because we have so many anchors. Okay, in case of GPS also, if you have happened to look at that app, right, if you can log some data, you will see that you are sometimes seeing 8 satellites, or you are seeing 10 satellites, or 7 satellites, right? We are not actually dependent on 4 satellites. Okay, in this case also, at the bare minimum we need 3 anchors, but nobody is telling us that that is the maximum. Okay, so more anchors you add to the system, it is the better. Okay, so hope this idea is completely clear, and you are welcome to have an implementation of this sort of on your own, right, so that you get used to the technique, right, and have more insights. Okay, so I'll go to the next part of the session here, is about how do you obtain such ranges. Now we have actually, till now we have assumed that by magic somehow we have gotten these ranges, and we were interested in solving the optimization problem. Okay, so till now we assumed the estimation of ranges. Okay, what we concentrated on is that given these ranges, these are given, okay, and the anchor locations are given. Okay, both of these things are given. How do you actually fuse such information or combine such information to solve the multilateration problem? So the method, right, or the set of techniques that we have just discussed throughout, right, the range equation and solving these range equations, these are known as multilateration technique. Multilateration. Okay, and if you are doing it with only 3 anchors, it is known as trilateration or triangulation. Okay, or triangulation, because there are just 3, like a triangle. Okay, you will hear such terms in like even movies, right? They say that by triangulation they have figured out the location of the car, right? Where the phone call, like some, maybe there is some robbery that has happened, and they were using a phone, right? And based on which cell IDs the phone was talking to, based on that you can triangulate the location of the car or that robber's car. Okay, so and if you are using more anchors, like 4, 5, 6, there is no limit. The general methodology is known as multilateration. Okay, and within multilateration we have looked at the nonlinear least square techniques, which was using this LM algorithm. We have looked at some of the matrix based techniques for linearizing, and we have also looked at the Taylor series, Taylor's theorem, right, and that was primarily in the last class while we discussed GPS, right. So you have some good knowledge about how to go about these range equations and solve them. Now we want to go one step lower, right? One step further in how do you obtain these ranges. Okay, later we will also show that okay, we don't actually have location of anchors, right? It might be the case. We will discuss this in short term, right? So, but how do you get these ranges? And in particular, we are going to look at wireless ranging, right? As I told you, it can be also acoustic ranging, right? You have a speaker, right, and you have a microphone. Okay, so if you have a microphone, it is possible to figure out this distance d. Okay, but I won't go into the acoustics ranging in these particular sessions. Let us concentrate on a more popular technique that is used by most of the indoor localization devices, which is based on RF modality, radio frequency modality, right? And I call it wireless ranging. So what exactly is the problem of ranging? The range is not directly available. What is available is basically the time of flight. Okay, so I'm going to give you some idea about what this time of flight means, and then I will revert back to some question answer session, right? And next class I'm going to cover a little bit more depth on what are the different errors that can happen with this TOF. TOF estimation we have to do, and in short, TOF estimation stands for time of flight. Time of flight. Okay, time of flight of what? A signal is actually traveling from the transmitter to the receiver, and that particular time has to be known. Okay, so if the signal is being transmitted at t is equal to 0, and in the receiver I am receiving the signal at time t is equal to 0.67. So, sorry, there is some noise from the background. Please try to mute yourself. So 0.67 is basically your time of flight, or TOF in short. Okay, and we also use the term time of arrival, or TOA. Okay, because the time of arrival of the signal. And what is distance, or what is the range? The time of arrival multiplied by the speed of light. So if you somehow know the value of time of flight to a pretty precise extent, multiply that with the speed of light, you get the distance estimation in between the transmitter and the receiver. Basic knowledge, right? Some knowledge about time and distance is necessary that you have from the 8th grade. So now, why is this sort of a tricky problem? I find a lot of noise. Please try to mute yourself. Whoever is doing it. Okay, so why correct estimation of TOF is necessary? The correct estimation of TOF is necessary.
Can I ask one question?
Yeah.
Yeah, sir. The methods we are studying are used for static node locations or mobile used for mobile nodes.
No, you can use the same thing for mobile nodes also, right? So it's just that you have to continuously keep updating the location of the device, right? So that is what you have to do.
Is there any difference between static node localization and mobile node?
Yeah, there are some differences. So what happens is sometimes in case of a mobile node, you don't have to independently compute the location of the device every time, right? So if you try to do this node localization as t is equal to 0, at t is equal to 1, it is not just going to vanish and go to a different place, right? It is going to be nearby, right? And that is what we call as tracking. Okay, there is a slight difference in between what we call localization and what we call location tracking. So location tracking refers to the fact that this device is mobile, right? And we are trying to keep track of the device with respect to time. Okay, so their assumptions are that we are not going to independently solve the location every time. We are going to look at the history. Where was the device at t minus 1, t minus 2, t minus 3, and based on that we can actually determine the location of the node. Okay, so coming back to the time of flight estimation, Okay, so NPTEL stuff, if you have access, right, you can figure out who is creating this noise. You can kindly mute that person. Okay, so let us try to understand why having a precise value of this time of flight is very important. This is primarily because uh, you are multiplying this by a very large number, which is speed of light. So if you make a mistake of even a few nanoseconds, as I kind of brought up in the last class, few nanoseconds, okay, what might happen is that since you are multiplying this by the speed of light, the distance will be varying by few feet. Okay, because light actually travels 1 feet per nanosecond. Okay, so this is going to be a very complicated problem if you cannot guarantee the precision of time of flight. And we are using very inexpensive devices. When you talk about IoT systems, we are not using a very hi-fi kind of a device that does not show clock drift and so on, right? We are not talking about microseconds, because nano to micro there is already a jump of 10 to the power 3, which means thousands of feet. Okay, forget about milliseconds. We are not talking about microseconds, because this is 10 to the power minus 9, whereas this is 10 to the power minus 6. There's already a 10 to the power 3 gap, right? And if you have a microsecond sort of an error in time of flight, you'll basically get thousands of feet of error. So I want you to understand the seriousness of the precision that we need, or even accuracy that we need for computing time of flight. Okay? So one simple algorithm is that we can simply start, right? We can start the sender. We can record that T sent. What is the timestamp of the packet that was being that when the packet is being generated and being sent, right? We can write that information T sent in that packet and send the packet. And in the receiver side, what we can do is that we can simply use the retrieve the time when the packet has arrived, right? That was the time when the packet reached the radio, record that time, and find out the time of flight rho as a difference in between T receive and T send. Okay, so the difference in between the T receive and T send is going to give me the value of time of flight, which is what we are trying to get at. Okay, so can somebody figure out what is whether this algorithm is all right, or whether this is something that we can use, or what is a glitch with this problem, and what is a glitch with this algorithm? We have a fairly simple algorithm. We send a packet from the transmitter to the receiver, we record the timestamps, take the difference of them, and be done. What's the problem?
Sir, maybe the transmitter and receiver are not synchronized time.
Very good. The transmitter and receiver will have different references of the clocks. In our GPS system, all the TXs, right, that had an atomic clock, right? And in this case, none of them has any different kind of synchronized clock. So the timestamp that will be recorded in the transmitter and the receiver will be very different.
And sometimes there is a noise is also there. So noise is not considered.
What kind of noise, though?
Like say the noise which is occurred during the medium.
But the medium noise, why do you think is going to affect the timestamp?
Okay. Time because it is the obstacle for the signals which will traverse through that medium.
So what might happen is that you don't receive the packet at all. Okay. So what we are trying to do here is not basically depend ourselves on the RSS or the received signal strength, right? What you are saying is the signal strength is going to be poor because of noise. The SNR is going to be low. Okay.
Yes, sir.
But what we are concerned here is that whether you receive the packet or not.
Okay.
If you don't receive the packet, it is a different story. But if you have received the packet, you can read the timestamp.
Yes, sir.
Okay. So it's like hearing your friend from a long distance. As long as you hear your friend, you know that your friend is alive, right? So whether it be the low voice or a high voice, okay? That is the difference. We'll see how signal strength based things is not always the best way to go. So that's why we are trying to learn this ToF based techniques. Okay, so somebody has already pointed out that what was going wrong, and once you tell your answer to yourself, right? Because we are all knowing each other. If, where you come from or what is your name, right?
So there is too much noise at back end. Can you
Yeah.
please mute Niveta?
That is Niveta. Niveta, can you also mute, madam?
Yeah.
Niveta.
So everything fine till now. So now there are several engineering challenges that are associated with this simple algorithm. Okay, so you have to kind of, we are going to go through these engineering challenges, right? Because now we have understood that this is an engineering problem that has to be addressed, right? Whatever I have told you earlier, if you go to a physicist, right, he is going to tell you that if you get the time of flight right, multiply that with the speed of light, you get the perfect value of distance, right? Then they are done. But now it is your burden as an engineer to figure out what is the value of time of flight. Who will tell you that? I mean, it's not that the radio is going to tell you, okay, this is my value of time of flight. You have to create a system that is accurate to the nanosecond scale, and at the same time it is going to give you an accurate value of time of flight. Okay, and then what are the different problems that could come up, and in the next session we are going to look at how to solve each of these problems. Okay, so when you say that record this t send into a packet, of course always think of a typical computer system where you have an operating system that writes values to the packets, right? You can, or the network interface card could be writing some values, the timestamp to the particular packet, right? So there will be a processing delay in between the timestamping the packet and actually sending it. Think about why I am bringing this kind of things up. We are not talking about microseconds, we are talking about nanoseconds. Okay, so the processing delay between the time stamping the packet and actually sending it could be quite large, and this can have an, like, we can record the value of time to be very imprecise. Okay, so when the packet or the signal actually left the radio and went into the air, okay, when you start transmitting, the ditto time that we require might be wrong. Okay, second is same for the recording. Whenever you are receiving the packet, I need to know that exact time when the radio has received the packet, because the radio might receive a packet, it might raise an interrupt, and that interrupt could actually wake up the CPU, and the CPU then thinks, oh, I have to record the time, now I record the time. But that entire time that was spent from when the packet has actually received the radio to raising an interrupt, waking up the CPU, that could take close to a microsecond, right? Okay, so it depends on what kind of sensitive device you are using. But since in this particular workshop we are concentrating on IoT devices, they are not going to be very much resourceful. Okay, very some dingy microprocessor or microcontroller will be there, and primarily it will be sleeping. You have to wake it up, right? Otherwise it is going to consume a lot of power. Okay, what are the clock offset in between these two devices? They are not synchronized, as somebody has told us, right? It is not synchronized, right? What is the clock offset that exists in between these two devices? Okay, so that is something that has to be corrected, right? Earlier we have corrected that, or you have incorporated this thing in the range equation itself, right? But in this case we can try out a clever mechanism in which the range could directly be estimated by incorporating the clock offset, right? We don't want to bring it up again in the range equation. Okay, and then can I have a way to know when the packet exactly arrived? Okay, so I am highlighting the word exactly because I want to know in a pinpointed fashion that when the packet has arrived. And of course time is continuous. I am not, you cannot do something that is beyond the capability of our transmission systems, right? Our granularity is nanoseconds, and if we can do something of, let's say, 0.1 nanosecond or even picoseconds kind of scale, we'll be more than happy, right? We don't want to go lesser than that, because we also have some kind of an expectation in terms of the position granularity, right? Because as I told you that as I have already told you that 1 nanosecond, sorry, so one nanosecond corresponds to 1 feet, right? So if you go to like a picosecond, which is again 10 minus 12, right? If you go to a picosecond, it is already 10 to the power minus 3 feet, right? So this is more than enough. We don't probably need something like this, right? Maybe we are happy with let's say 0.1 feet, right? So in that case, 0.1 nanosecond might suffice, right? So this is the granularity of the word exactly, okay, because the term exactly is sort of unscientific, right? So if we try to quantify what exactly means, this is the expectation that we have from the system, and that is why I put it up as an engineering challenge. Okay, so what is the methodology that we are going to follow in order to derive this value at a granularity of like nanosecond or a little bit less than that? Okay, so that is going to solve the problem of 1 and 2. So 1 and 2 timestamping I don't have to do, okay, but it does not solve the problem 3. Okay, problem number 3 is basically who will tell me what is the clock offset between these two devices, because these devices are continuously drifting, right? The clock is continuously drifting. If you ask these two devices to count from 0 to let's say 1 million, right? That means basically you will have 10 to the power 6 uh, clock pulses, right? If you count, if you increment a value of register every with every clock pulse, so 10 to the power 6 clock pulses you are going to have, right? And for doing that, if you are using some a processor which has a clock rate of tens of megahertz, okay, so you will do it in some like few milliseconds, right? You can do that in few milliseconds. Okay, what you will see that the time of completion of this counting job for these two devices will be different. If you think, if you give it a count from let's say 0 to let's say 10 million, okay, so for simplicity it will be let's say 0 to 10 million. You have to count from 0 to 10 million, and you are using a 10 megahertz clock, which basically means that you are actually executing 10 million clock cycles per second. And if you are incrementing the value by 1 for every clock pulse, then you will basically have an entire second to do this entire operation. Okay, but in real life, if you actually do this, right, perform this operation, you will see that you will not have a value of exact 1 second. Okay, either way, right? If you run it for 1 second, you will not find an exact value of 10 million in both of them. It will be plus minus something, some delta. It could be plus minus 100, plus minus 200, right? Because sometimes the clock might run fast, sometimes the clock might run slow, and that is a hardware error, like hardware manufacturing artifact, right? Because the way the hardware, the silicon has been produced, the oscillator inside the microcontroller has been produced, it will have some kind of a clock drift, and you cannot do anything about it. So it is your burden now in order to take this hardware which is not perfect and try to incorporate intelligent ranging algorithms so as to take care of 3 also. 3 in the sense challenge 3. Okay, so I will just keep it till here, right? Because there will be otherwise too much things on a single day. So think about this last part of the talk, right? Mostly why ToF estimation is actually a hard problem, and whatever we have already learned, like geometric dilution of precision, solving the nonlinear least square optimization problem using the LM algorithm, and so on. Okay, so if you have any questions from the previous class or today's class, maybe we can use this 10-20 minutes time we have for some discussion. Okay, so maybe we can, if you have questions, please turn on your mic and ask questions.